In MCQ 9, continuing with the theme of chemical energetics, so for this case here, we are given the value of the standard enthalpy of combustion of methane going at negative 890 kJ per mole. And we need to find out what's the enthalpy change of vaporization of water going from liquid water to H2O gas. And we are conveniently given an average bond energy value. Now, usually this kind of table, after it was being given, is usually a very big indication that we have to employ enthalpy change is equals to bond breaking minus bond formation. Usually that's the case here if the table is given. So for that, we'll start off first by writing the enthalpy change of combustion of methane. So we have CH4 gas plus 2O2 gas. And this gives us CO2 gas plus 2H2O liquid. Now you can see that this H2O liquid is actually the important part here because it allowed us to link towards the vaporization of water. So if I were to have this of going through 2 times the vaporization of water, again a 2 is placed in front because per vaporization only involve 1 mole of liquid water. If I have 2 moles of liquid water, I need to multiply this by 2. This actually allows me to obtain 2H2O gas. But because the carbon dioxide did not go through any reaction, I will just inherit it to be a CO2 gas over here. Now for the next step here, we just want to find out what is the enthalpy change from the top portion towards the bottom portion. I can treat the top portion as going through a very simple bond breaking process, and the bottom portion that involve the vapor and carbon dioxide to be as products going through bond formation. And this could have been calculated by using the table given over here. So enthalpy change of reaction, dealing first with the reactants. For CH4, we have a total of 4 CH bond, 4 times 410, plus for O2, each of them there is 1 O double bond O, but for 2 of them, it will be 2 times 496. Now dealing with the bond formation, minus it off, for CO2, we're going to have 2 C double bond O going at 805 times 2, plus for H2O, per unit H2O contains 2 OH. So if I have 2 of them, that will be 4 OH. That will also be 4 times 460. And this gives us a value of negative 818 kilojoules per mole. So filling in the values in the table itself, we have a negative 818 kilojoules per mole, the enthalpy combustion at negative 890 kilojoules per mole. What we can now do is to find out which of them is the start point of my Hess diagram and which is considered to be the end point of the Hess diagram. Now, mentioned in class, for the start point, we're looking for objects that has only arrows pointing out of it. And for the case of the end point, they are the lines in the equation that only have arrows pointing towards it. So you can see that over here, for the one at the bottom here, it only has arrows that's pointing towards it. I'll call this to be as the end point. And for the case on the top left, it only has arrows that's pointing out of it, so I call this as my start point. So one possible route to go from the start to the end is actually to go via negative 818, which is the bond break minus the bond form. But an alternate route to reach there is to go with the enthalpy of combustion of your methane plus your 2 times enthalpy of vaporization of water to get back to the end point. So for this, we can use Hess law to solve it. So by Hess's law, I'll say that negative 818 is the same as negative 890 plus 2 times standard enthalpy vaporization of water. So finishing off very quickly, the answer over here for enthalpy vaporization of water should you solve the equation, you should end off with a value of positive 36 kilojoules per mole. Just be careful and take into account that there is a 2 in front of the enthalpy vaporization of water. For your final answer, you have to divide by 2 to get positive 36. And therefore, the correct answer for this question here is C.